Alright, so now let's move on to the binary eutectic systems. Okay, so as I've already mentioned to you just now, the binary eutectic systems can be divided into two categories. The first one is the eutectic with no solid solution. Alright, and then the eutectic with limited solid solution. Okay, so the one with the no solid solution is where there is a two-phase field, okay, for pure solids A and B, and where the two components A and B cannot dissolve in each other. All right, so that's the no solid solution. Okay, but then for the eutectic with limited solid solution, okay, is where the two components A and B are partially soluble in each other. All right, that means, okay, it can mix together but in only a certain amount, all right, of A into B and B into A. Okay, okay, so if we are looking at the phase diagram here, okay, let me just check. Okay, let me draw the outline of this phase diagram. Okay, again. Right. So let's say this is how it looks like, okay, roughly. Right. So the axis, okay, will be the same. Okay, the y-axis, okay, is the one for temperature, and the x-axis is the one for the composition. Okay, so normally it is expressed in the weight percentage. Okay, and at one end, okay, we'll have first component A, and then at the other end, okay, we have the component B. All right, so we know that at this point it's 100% A, and the other point is 100% B. Okay, so if you can recall back, okay, the binary phase diagram for the isomorphous systems, okay, it looks very simple. We only have like three phases, okay, within the isomorphous phase diagram, okay, which is the liquid plus solid, and all the solid region. Okay, but then for a binary eutectic phase diagram, okay, with limited or partial solid solution, okay, we have like more phases coming in. Okay, but again, okay, if you look at the top of the phase diagram, okay, it's still the all liquid phase, right? And then because of the partial solubility between A and B and B into A, all right, so we can actually divide the phase diagram into like two sides. All right, so one side here, one side here, okay, is where we have the alpha. So the phase in between is liquid plus alpha, and on the other side here we have beta, right? So the region in between is for liquid plus beta, and the last region here, okay, or the phase here is for alpha plus beta, right? And then we have the phase boundaries. Okay, so this is the liquidus line, all right, and this is also the liquidus line, right? So liquidus line, okay, that separates, okay, between the liquid and the liquid plus solid region on both sides. Okay, and then we have the solidus line. All right, so previously we already looked at the solidus line. Okay, below which, okay, it separates the liquid plus alpha with the alpha region. Okay, and then this is the solidus line, okay, on these sides, okay, where it separates the liquid plus beta and the beta region. Okay, but then here we have another phase boundary, okay, that separates the single solid, okay, with the two solids region here. All right, so this line, okay, that separates alpha and alpha plus beta region is what we call as the solvers line. All right, so same thing goes on this side. Okay, this is the solvers line. All right, so if you look at the liquidus line, okay, because above this liquidus line everything is in liquid, okay, so this liquidus line is actually the melting point, okay, for any combination of alloys, okay, consisting of element A and B. Okay, so what it means by that is that, okay, let's say we have this line. Okay, and this line consists of, let's say, 20 weight percent B, okay, and 80 weight percent A. All right, so this point, okay, above which everything is in liquid. All right, so it means, okay, this point, okay, if we look at the temperature here, T1, okay, so T1, okay, will be the melting point, okay, for C0, okay, which is the alloy composition here. All right, and then if we have like a different composition, okay, so let's say we have another composition of alloy here. Okay, so let's say at this point it's 80% B, okay, because it's closer to the 100% B, right? Okay, and at this time it's 20% A. All right, so the melting point for the alloy that consists of 80% B and 20% A is this temperature here. So let's say this is T2. Okay, so T2 is the melting point, or Tm, okay, for the C0 here. All right, so any combination of alloys, okay, that you choose, okay, so this line, okay, of liquidus line, okay, all those points, okay, will be the melting point for the alloy composition. All right, so it varies, okay, along the line. All right, okay, so I guess I already covered that. Okay, so okay, let's have a look at a specific binary eutectic system, okay, consisting of copper, okay, so this side is copper and this side is silver or argentum. Okay, so for example, in a copper silver system, okay, we have three single phase region. Okay, the single phase region, okay, is one is liquid, one is alpha, and one is beta on that side. So as I already mentioned to you just now. All right, now the one thing that I forgot to mention just now, all right, is the solubility limit. Okay, so now let's have a look. All right, this point and this point. Okay, so this point is actually the solubility limit of B in A. Why? Because this point is actually closer to 100% A. Alright, so at this point, okay, we only have like small amount of B, okay, and more of A. So A is the solvent, B is the solute. Alright, so this is the maximum solubility limit of B in A. Okay, and vice versa, this is the point of solubility limit of A in B. Okay, so this is the maximum solubility limit. Okay, because this point is actually closer to 100% of B. So at this point, B will be the solvent and A will become the solute atoms. Okay, so let's have a look. Alright, and TE. Okay, so TE is the what we call as the eutectic temperature. Okay, so the whole system is known as the binary eutectic system. Okay, so binary is referring to two components. Okay, and the eutectic here is referring to the special composition with a minimum melting point, a melting temperature. Okay, so if you look at the phase diagram, okay, so let's just go at this point again. All right, all of the composition, okay, of alloy that you choose, so from the liquid phase, okay, it will cross these boundaries, okay, before it enter the two phase region of liquid plus alpha on these sides, or it cross this boundary to go into the liquid plus beta region on this side. Okay, so any composition of alloy that you choose, okay, it will pass through these two lines, okay, of liquids, either on the left hand side or the right hand side. But there is only one composition in particular, right, during solidification, means, okay, from the liquid form, okay, after it actually surpass certain temperature, okay, it will completely instantaneously solidified without having to go through the transition phase of liquid plus solid. All right, so the composition, okay, is called the eutectic composition. All right, so if you look at this line here, okay, so if we have a composition of alloy, okay, goes along this line, so let's say this is CE, okay, so from liquid phase, okay, at this point it's all liquid, okay, and it solidifies, so the temperature decrease, okay, once it pass through this temperature, okay, it will go from liquid to alpha plus beta region. Okay, so it's not going through the transition phase, either the liquid plus alpha on the left hand side or the liquid plus beta on the right hand side. Okay, it will go straight from liquid to all solid. All right, so this kind of composition, okay, is what we call as the eutectic composition. Okay, and the temperature at which, okay, it cross from the liquid to all solid is known as TE, or the eutectic temperature. Okay, and within a binary eutectic phase diagram, okay, so this kind of eutectic composition occurs and only at one specific composition of alloy only. Okay, and it also occurs at one specific temperature only. All right, so the temperature is called the eutectic temperature and the composition is called the eutectic composition. All right, okay, so basically, okay, we can write down the reaction, okay, of the eutectic, okay, as this. Okay, so this is the general ways, okay, in which you can express the eutectic reaction. Means, okay, from liquid, okay, upon solidification, okay, or it can be vice versa upon heating, okay, it change to alpha plus beta. All right, so it doesn't go through the transition phase of liquid plus solid. All right, so for this particular binary eutectic system consisting copper and silver, all right, So since all of this eutectic reaction occurs at a very specific composition and very specific temperature, we can actually figure it out. All right, so let's have a look. So Ce for copper and silver system occurs at 71.9 weight percentage of silver. So now you can see that it says there. All right, when it's in liquid form, when it's all liquid, we have 71.9 weight percent of silver. All right, so upon cooling, it will become alpha plus beta. All right, so 8% here is this point, referring to the maximum solubility limit of silver in copper, and beta is here at this point, 91.2 weight percent silver. This is actually referring to the maximum solubility limit of copper in silver. All right, and it occurs at a specific temperature of 779 degree centigrade. So it's here 779 degree centigrade. All right, so the composition is 71.9, the temperature is 779. All right, so different combination of components will have different eutectic temperature and different eutectic composition. All right, this is an example on how you can determine that four important information from the phase diagram. The phase present, the composition, and the weight fraction, and also the resultant microstructure. So the same rule applies. We have to use the level rules. It's just that one thing, the level rules is only applied in a two-phase region. So it does not apply in a single phase region. That means if it falls in all liquid region, so it's 100% liquid, so there's no need to do the level rules. And then this is an example of the microstructural developments for different sets of alloy composition. So for alloys of which C0 is less than 2 weight percent of stannum, for plumbum and stannum phase diagram. All right, so for this particular combination of alloys, so it will go through a few phase, from melting point. So we have like it goes from liquid, through liquid plus alpha to alpha. So when it's all liquid, so we just draw it like that because it's 100% liquid. And then it goes to liquid plus alpha, so there'll be some solidification of alpha takes place. So this is alpha and the rest is still liquid. And then upon completion of solidification, so everything will become alpha. All right, and the next set is the one that cross 1 2 3 4 regions. So it goes from liquid here to liquid plus alpha here. So this, let's say this is the C0. So upon cooling, so it goes from liquid to liquid plus alpha. All right, and then it goes to this area of alpha, and then as the cooling keep on forward, so it goes to the alpha plus beta region. So from liquid, it's the same thing goes, it's all liquid, so 100% liquid, and then it goes to liquid plus alpha again. It will start to solidify some of the solids. So it's alpha and the remaining is the liquid, and then it goes to alpha, means the solidification already completed. But then some transformation can also be happening, okay, even though the solidification already completed. So when the temperature decrease more towards the room temperature, all of this alpha will rearrange themselves. Means, okay, the solute atoms, okay, within the solvent will rearrange themselves, okay, and there will be some precipitation of beta. All right, so we will have alpha, okay, which already solidified at the first place, okay, and then we have like flakes of beta coming in. All right, the precipitations of beta. So the flakes here is beta. All right, so that's how it looks like, okay, the resultant microstructure. Okay, so when you're doing the analysis, the phase analysis, okay, you're going to provide for info, right? Okay, the phase present, the composition of each phase, okay, the weight fraction of each phase, and number 4 is the microstructures. So you have to be able to draw the correct microstructure. Okay, so which one, okay, between this one and this one and that one and the last one, it depends on the temperature at which, okay, you are taking consideration of the phase analysis. All right, so there are two things, okay, that you have to be aware of, which is the composition of the alloy and also the temperature. Okay, so it will actually dictates the microstructure, okay, which one, okay, that you have to draw. All right. And this one is for the alloy composition at eutectic composition. Okay, so the development of microstructure at eutectic composition. Okay, so since, okay, it doesn't go through the transition of liquid plus alpha or liquid plus beta region, okay, so it goes straight away from liquid to all solid. All right, so when it's changed, okay, to alpha plus beta upon solidification, okay, so this alpha and beta, okay, comes in the form, okay, of a lamella structure. Okay, so this is called a lamella structure, where we have an alternate layers of alpha and beta within the grains. Okay, so let's say the blue is alpha and the red is beta. Okay, so it's an alternating layers of alpha and beta. All right, so this kind of microstructure is what we refer to as the lamella structure. Okay, so this is how it looks like. All right, and then we have the most common alloy composition, okay, that can occur on the right hand side or the left hand side. Okay, so which across, okay, the three region of liquid, okay, and the transition, okay, either liquid plus beta or liquid plus alpha, and upon solidification it goes to the alpha plus beta region. Okay, so when it's all liquid, so it's very easy. So okay, you can just draw it blank like that, and then when it goes into this area of liquid plus alpha, so you know the alpha starts to solidified, but the remaining is still in liquid form. All right, once it cross the boundary here, the temperature, okay, so it all turns to alpha plus beta. I mean the remaining liquid, okay, will be turning into alpha plus beta. All right, the alpha that comes, okay, before that, okay, that before you cross this line, okay, which is the eutectic temperature, okay, will remain. So that's why here you see, okay, you have the alpha here, okay, which is referring to the alpha before you cross the eutectic temperature. So this is the eutectic temperature, TE. All right, and the alpha within the alpha plus beta is actually different. Okay, so one is in the form of lumps here, okay, but alpha plus beta, the alpha in alpha plus beta is a lamella structure, so it has to be an alternate layer between alpha and beta. So this is how it looks like. Okay, and when we are looking at the phase diagram just now, okay, so if this is the line for the eutectic composition, this is the eutectic composition, Okay, so basically there are two parts of the first diagram. Okay, so before the eutectic composition is known as hypoeutectic composition, and after the eutectic composition is known as the hypereutectic composition. Okay, and these are the phase diagram with intermetallic compounds. Okay, so intermetallic compound exists as a line on the diagram. Okay, so this is the line. It doesn't exist as an area. Okay, because of its stoichiometry, that is the composition of a compound is a fixed value. Okay, so instead of eutectic, okay, we have other reactions too, okay, that can be exist, okay, on a phase diagram. Okay, so we also can have eutectoid. Okay, so eutectoid occurs when one solid phase transforms to two other solid phase. Okay, so we'll be looking at this further later on, okay, in the iron and iron carbide phase diagram. And then we have a peritectic reaction. Okay, so the peritectic reaction is when we have liquid and one solid phase transform to the second solid phase. Right, so if you look at this particular diagram, okay, here, okay, is where the peritectic reaction occurs. Okay, so if you look at that spot, okay, it looks something like this. All right, so this is delta, this is gamma plus liquid. Okay, so if you look back at the definition, peritectic is where the liquid and one solid phase transform to a second solid phase. Okay, so if you look here, one solid phase, okay, so this is one solid, okay, and one liquid transform into one solid. Okay, so it's gamma plus liquid upon heating, upon cooling, become delta. Alright, so which is at this point. Okay, and then the other one, okay, we have the eutectoid transformation. Okay, so here, okay, if we just enlarge the whole thing here, okay, so down here is the gamma plus epsilon, okay, and here is the delta. All right, so if you write down the reaction, okay, it's delta, okay, upon cooling and upon heating, okay, it becomes gamma plus epsilon. Okay, so this is the eutectoid composition and this is the peritectic composition. All right, okay, so I guess next is the iron and iron carbide phase diagram. All right, so I'll cover that in another video. Right, so I think that's it for this part. Okay, I'll see you in the next video, inshallah. Assalamualaikum.